Good afternoon. Now we're continuing with our discussion of gravitation, specifically general relativity, trying to keep it casual. It's pretty much unprepared and spontaneous. I tried to do some good calculations, but time is limited. So big calculations, I haven't done many of them, if any. But I will do one, not today. I'll do some calculations with this as an example. It's hard to see this picture otherwise. What we're going to talk about are contravariant and covariant components of a tensor or vector, first introduced by James Joseph Sylvester in 1853. Okay, now roughly speaking, contravariant and covariant components, let's do this. Here are some coordinates like, let's say, x and y coordinates. We'll look closely at tangents to these coordinates, or specifically, locally flat coordinates. Locally flat coordinates, x and y, is what we get when we look more closely in here between these tangents. So, how can I specify a point with respect to these two coordinates? We're used to dealing with x and y at angles like this. X and y being orthogonal coordinates. These ones don't have to be. So if I have a point here, or it could be the position of a vector. Let's say it's the position of a vector. Actually begin with a point. The coordinates of that point can be specified in two different ways. I can measure from here to here, perpendicularly from the x and the y axis. So I would be specifying the point with covariant components with respect to the axis here, and it could be a position vector, the components of a position vector. Let's take the same two coordinates over here. And let's take the same point. Let's specify it with a slightly different way. I can measure a line with a line using a coordinate line parallel to y and another one parallel to x. I can still find that point, but this is no longer a right angle. This is no longer a right angle. These are the contravariant components. The same position vector. Now this position vector has something which cannot change. The length of that vector cannot change no matter what way we construct the coordinate system. So the length of a vector is said to be invariant under the transformations between the contravariant and the covariant coordinates, and even if seen in a different coordinate system, the length is going to be an invariant, and an invariant is a number. It's a scalar. A scalar function spits out a number. That's just a number, and the number must be valid even if I transform to a different set of coordinates. For example, between polars and Cartesians, it must be the same number, right? When we transform from one set of coordinates to another. And that's what we're doing all the time here. So, contravariant components, covariant components. Covariant is the word. So let's clean the board. I'll let you catch up with that. Okay? Because because I only have one board and I need all the space, there's another rule though. Once I say something, you've got it. Contravariant and covariant components, James Sylvester, 1853, you've got it. Okay, this I was fiddling around with. Now let's start getting used to our notation, because the notation is part of this science. I keep dwelling on that. Specifically, I talked the last time about the Einstein summation convention and the notation. Let's just talk about two different coordinates, x and y, in polars. X is r sine theta, y is r cos, y is r sine theta, it doesn't matter. So we'll say that x is f of r theta, and y is f y of r theta. Two different functions, x and y. But we could call this x1, because that's what we tend to do in this system. When we're manipulating these, we use the minimum amount of notation. X at 1, x2, x and y, f of x. But we'll say that's x of x instead of f of x. And y, we'll call it y2. In other words, it's a function of r and theta. And not only that, we'll label it this way. In other words, we'll label the x's as x1 and x2, the Cartesians, and the polars we'll label as x1 as well and x2, but with a dash. Specifically, it's like this. And this is going to allow us to make our notation much more compact. Now, let's take a vector, actually. I'll specify a vector with contravariant components. And there's a transformation rule between the the new components and the old components. It's a contravariant vector. If this is the free index, it refers to that one there with the dash upstairs for contravariant, and the old components of the vector were the a mu. So this is how contravariant components of a vector transform. Now watch my mu's. These two mu's are repeated, so that means summed over. We're going to work in 3 space. So it's like that. We're summing over I from 1, 2, and 3. Okay? Now, if the covariant components are under investigation, this is the way they form, with the dx mu downstairs. Now, we have to think about what we mean by this. That means we have functions, x mu, specifying this partial derivative, and functions x mu dash, and functions x mu satisfying this one. In other words, suppose we were talking about Cartesians and polars with their respective transformations. These would be the x mu's, and these would be x mu dashes. In other words, functions of the transform coordinates, r, theta, and phi. We want to get from x, y, and z to r, theta, and phi. Okay? We'll get to that in a minute. These are the rules. Contravariant. And covariant. Okay, this is just to let you know how our notation is working. So, I'm going to get rid of this in a second. I'll just put our rules up on the board. And we're talking about the components of a vector. Now watch where I'm putting my dashes. Dash there means this is a free index. Repeated, mused. That means they're summed over. The dash has to be up here. That's our transformed vector, and this is our old vector. These are the ones summed over. So I leave that there. And we'll look at an example. Now we want the contravariant components of A mu dash. Well, they would be the components in here because we're not writing out the whole vector, but it would be for the vector A would look like this. And A mu are its components, right? We're not looking at the bases, we're just looking at the components themselves, okay? Now really, these numbers, these should be upstairs. So we want the contravariant component AR, which is the same as A mu dash, or mu equals 1, or simply A x1 dash. So we need A x1 dash. We want to find that. Find A x1 dash. Well, it's going to be the rule for transforming a contravariant vector. There it is there. So we sum over the x mu's. And we shouldn't have put that x mu in there. So it's going to be this. So that's what's going to be the whole case. So I'm just going to look at let's have a look at it step at a time. Okay, so we get this into our heads. AX1 dash is also A of R. So if I've got that in our heads, we can take a photograph picture of that and get rid of this so that I can carry out the calculation. Now the x1 dash over the x for u1 dash equals r. Now x dash of r is going to be this one of here. That's the transformation function that gives me what r is. R is x1 dash. Theta is x2 dash, and phi is x3 dash. Okay, so we go. The x over r1 dash over dx is just take the derivative of this guy with respect to x. Now differentiate inside in the bracket first, okay? Or you can do it either way. Differentiate the bracket first and we get half times x squared plus y squared plus z squared times a half minus 1. Half minus 1 is minus a half. And differentiate inside the bracket. This is the chain rule, by the way. That's what we're doing, okay? We're just taking the derivative of the what? dr by du times du by dx. Now times 2x. du by dx, the x squared by dx is just 2x. Squared plus y squared plus z squared is simply x over r. Here's r, x over r. Now we have to add up the components of the dx dot by dx, by dy, and by dz. But look, it's the same form. See? So when we add them all up, each one will be the same. Just replace y next time. And we get x plus y plus z r for these guys. But wait a minute, I have to multiply by each component of x as well. So let's put that in. Now I haven't specified exactly what ax, ay, az is, but if we do this, we notice something. It's a dot product between the position x, y, z over r, like a dot x over r. Which is just the same as a position vector, unit vector, in the r direction, okay? All right, so that's the contravariant component for a mu dash when mu is 1. Now the other ones are a little bit more complicated, and I wouldn't have time to do them in YouTube because I have the 10 to the minus 1 in here. It'll be a similar situation. I want to do an example using covariant components. Covariant, okay. I'll let you get a hold of that. That was a contravariant case. Now to get covariant components, I use the original functions. I use these transformations. I've already used these ones. I don't need them again. Get rid of it, make space. So now we take these functions as being x1, x2, and x3 for x, y, and z. For this one here, the x component,